Welcome to the next module of the course. In this module, we'll talk about some of the benefits and limitations of patterns and frameworks. We'll start by focusing on the benefits and limitations of patterns. It would be great if I could tell you that using patterns will make all your software development problems magically disappear. But of course, that's not the case. However, there are a number of benefits that patterns provide to the software development process, and let's start by summarizing those. One of the key things that patterns help with is to capture and abstract recurring software roles and relationships to facilitate systematic reuse of successful designs. I had my first major experience with this benefit back in the early 90s. I'd been developing software components and frameworks for networked and concurrent systems, and I developed a framework called the reactor, which essentially allowed you to abstract away from low-level synchronous event demultiplexing functions like select or poll and provide a more object-oriented, extensible, and easy-to-use framework where you'd register event handlers that would get called back when events occurred and had been detected by these low-level operating system mechanisms. And I wrote several papers, one of which you can read at the URL below, and had a fair amount of experience developing this particular way of handling events in a network system. When I would go out and explain this to people, however, they would always get wrapped up in the implementation details. We'd be talking about using arrays or file descriptor sets or linked lists and so on, and we'd often miss the more fundamental design abstractions. When I became a reviewer for the Gang of Four book and learned about patterns, I suddenly realized that I could recast my reactor framework in the form of a pattern, thereby helping to more effectively reuse the key roles and relationships that were endemic for many different realizations of this particular approach. And so from there, the reactor pattern description was born. You can find a description of this pattern at the URL below, and of course it also appears in various books, such as the POSA 2 book. The key benefit of looking at things from a design pattern perspective was that it helped us to be able to de-emphasize the unessential implementation details and focus more on the key abstractions that application developers would use to shield themselves from the low-level details of event demultiplexing mechanisms provided by the operating system. Patterns also help to record engineering trade-offs and to be able to systematically evaluate design alternatives to thereby enhance development and sustainment of software systems. Towards the end of the 90s, I got my first real experience with these benefits of patterns. At the time, we were developing an open source implementation of real-time Corba called the ACE orb, or DAO for short. And we were confronted with some design trade-offs having to do with the way in which we would structure the underlying concurrency mechanisms for our real-time Corba implementation. And by that point, I was pretty well versed in patterns, but I'd been looking at them primarily in terms of design abstractions. And what we were confronting here was, of course, about design, but it was also about performance, predictability, quality of service, avoiding various hazards of real-time programming, such as priority inversion. And so we took it upon ourselves to look carefully at some of the design patterns available at the time to determine which of them would be most appropriate to structure the trade-offs between different implementation and design approaches for our implementation of real-time Corba. The two alternatives that we ended up settling on were known as the half-sync, half-async model of concurrency, which is based, not surprisingly, on the half-sync, half-async pattern. We'll talk more about this pattern later, but in a nutshell, this pattern basically makes it possible to separate your software into several layers, one of which waits for events in a single thread, and then passes through a synchronized queue up to a pool of threads that can process the events concurrently. And the benefit of this particular approach is it's very scalable. The downside is it tends to incur some overhead for context switching, synchronization, data movement, and so on. The alternative approach is based on something called the leader-followers pattern. And this pattern allows a pool of threads to take turns waiting on an event demultiplexer for activity to occur. And when activity occurs, the leader thread is responsible for handling the data associated with that activity, while one of the follower threads becomes the new leader. The benefit of this particular approach to concurrency is that it makes the predictability much higher, and it reduces context switching, synchronization, and data movement overhead. The downside is that it's harder to implement certain queuing mechanisms because of the way in which the pattern structures the various roles and relationships. What we did ultimately for our particular use was choose the leader-followers pattern because the real-time predictability and performance was paramount for the sponsors we were working with. But the key point here was we were able to use patterns as a way to systematically evaluate the trade-offs between alternative approaches and be able to document them in a way that could be usable not just to build the software, but also to serve as a guide for future sustainment and evolution by other developers who might not have remembered the original reasons why we made the decisions we did. There's a paper here at this URL that you can take a look at that provides more information about these trade-offs between the two patterns. Another benefit of patterns is that they help to improve a shared design vocabulary between members of a team, thereby making it easier to understand the architecture and the design, make it easier to do engineering and re-engineering efforts, make it easier for the team to communicate because they have a common way of expressing the key design abstractions in their particular design space. I learned this lesson many times throughout my career. When we were building our implementation of real-time Corba, there were lots of other implementations of Corba we were competing with at the time. And many of those implementations were built by teams of developers who had a lot more experience than myself, my grad students, and my research staff. But because we had based our solution on a family of patterns, and we had documents, papers, books, annotated source code that captured those patterns clearly, and we had frameworks like ACE that embodied those patterns, it made it possible for us to be able to develop very efficient, very portable, very predictable middleware much more rapidly and at much less cost, thereby allowing us to compete with other groups that didn't have the benefit of a pattern-oriented software approach to what we were doing. If you take a look at this URL, you'll find many other papers that document our experiences using patterns to convey the design of our software to other people. Another benefit of patterns is they provide a basis for automation. In earlier sessions, we've talked about the proxy pattern and how the proxy pattern is a great example of a recurring theme throughout the history of software development and programming languages and computer science, where conventions and patterns at one phase that prove useful later become automated in order to be able to provide built-in language features and tools that do a lot of the work more efficiently than having to write all the code manually. Certainly, this is one example of how patterns provide the basis for automation. There are also other examples that are becoming popular as well. Examples based on paradigms like model-driven engineering, which use so-called domain-specific modeling languages to capture key structures and behaviors in a domain-specific way using tools that can then perform various kinds of analysis and synthesis of code without requiring the application developers to have to write all that code manually. Now, obviously, not all patterns lend themselves to automation, but for those that do, and for those paradigms like model-driven engineering that support such an automation, it's a very powerful technique to improve productivity and reduce many of the tedious and error-prone software defects and errors that occur when writing code by hand. There's an article that I wrote a number of years ago that describes model-driven engineering and places it in the context of middleware and computer-aided software engineering and patterns that you might want to take a look at for more information on this topic. Another benefit that patterns provide is they help us to transcend biases that often arise when people are overly wedded to a particular programming language. If you get a bunch of software developers together for any length of time, one of the most interesting and controversial topics you can bring up is their favorite programming language. Just as people around the world debate ad nauseum their favorite basketball player, or the greatest football or soccer player of all time, or the greatest guitarist or singer, so too do people like to debate their favorite programming languages. And that's all great when it's in good fun. But oftentimes you find people who get so wrapped up in the details of their programming language and the features of the language and certain ways in which they can express certain concepts and design intent through a particular set of syntax and semantics that they lose sight of the bigger architectural issues. And this is where patterns come in so handy, because patterns often help us to emphasize what's really important, which are those recurring roles and relationships at the design phase, which can often be implemented in many different programming languages and with many different implementation techniques for many different purposes. But focusing on the design helps us transcend language-centric bias and myopia. The other main benefit of patterns is they help to abstract away from non-essential implementation details at the right point in time. For example, in the design phase, it's not always the case that you have to be overly concerned with what operating system platform you're going to run on, or whether you're going to use an array versus a linked list to implement some of the internal data structures of a reactor. Those are decisions you can defer till later on in detailed design or in the implementation phase, or even during maintenance and sustainment if you architect your system properly. And the nice thing about patterns is they help to separate concerns. They help to focus on design as design, be able to communicate more effectively so people can think more clearly about how their software needs to unfold without being distracted by lots of issues that won't become necessary to consider until further downstream. There also, of course, are limitations with patterns. One of the main limitations with patterns, of course, is that even though they help you become a more effective architect and designer, they help you to communicate more effectively with your team, they may even make you more fun at parties, but they require human effort to implement. Patterns don't write the code. Someone has to write the code that embody those patterns. And that can often be a Sisyphean effort that is very tedious and error-prone. I remember many times as we were developing our middleware over the years, we would apply certain patterns that we had learned about in the literature or we ourselves had discovered and documented through previous effort. And even though we were very glad we had the patterns to guide us, inevitably there would come a time when implementation complexity was the main challenge of our development effort. Remember when we were developing some of our middleware using this leader-followers pattern I mentioned before. And even though we understood the pattern, as we started to implement the pattern in various kinds of real-time contexts, where we had to move information between threads running at different priorities, there were some pretty nasty implementation considerations. And so even though the patterns helped to guide us, we still had a lot of work ahead of us. You might want to take a look at the URL here to learn more about leader-followers and some of the many different variations you have to be considering when you try to apply it in a range of different application domains. Another limitation with patterns is that in the wrong hands, patterns can be deceptively simple. In the right hands, of course, in the hands of an expert, in the hands of a senior architect, patterns are extremely helpful to separate concerns, to move key challenges and key solutions at the right point in the right phase of the software lifecycle. But in the hands of an amateur or a dilettante, these patterns can often lure or lull people into thinking something hard is actually easier than it really is. Many times I've been working on projects for mission-critical, distributed real-time embedded systems. And often I'm surrounded by fantastic architects and developers who understand the proper use of patterns. Of course, there's always the pointy-haired boss who doesn't really understand the complexities of software, who hears a part of the story about how patterns can simplify development, and who therefore comes to the conclusion that we can simply apply patterns, get rid of the need to have those expensive A-team members, and instead use junior developers, or even worse, start trying to outsource the development to off-the-shelf technologies that are very inexpensive, that appear at face value to implement the patterns, but in fact don't adequately address many of the subtleties, many of the quality of service considerations, and so on. So you have to be careful. Just because you can say things like broker or proxy or publisher subscriber as a design team doesn't necessarily qualify you to understand how to apply these techniques effectively for many of the more mission-critical environments, where the right answer that's delivered too late becomes the wrong answer. Another related challenge with patterns is that limited knowledge of patterns can often constrain the design options of an individual or a team. Many times I've gone into projects as a consultant where the team took some patterns training several months or years ago, and they probably learned about some of the patterns in the Gang of Four book or maybe one of the POSA books, and they've been conscientiously applying those patterns to their code. And when I come along at some point for a review or some kind of analysis, people will sometimes pull me aside and say, before we learned patterns, design was a creative activity. We could do all kinds of interesting things. We could solve the problems in the way that made the most sense. But since we started to study patterns, we feel like we're locked into a Procrustean bed of very limited approaches. And we keep seeming to apply, say, the broker, or the proxy, or the adapter, or the observer, or the reactor. And those are the only things we seem to be able to do. And our ability to do more creative solutions that really meet the needs of our sponsors and customers seem a lot harder than they used to be. And whenever I hear that, I sort of chuckle to myself. When I was growing up in high school, I played soccer, what the rest of the world calls football. And I lived in the Washington, D.C. area of the United States. And many of the people who I played soccer with were my friends from all around the world. It was a very cosmopolitan place to grow up. People were there from Asia, they were there from South America, they were there from the Middle East, they were there from Africa. And we all had a great time playing together as 15 to 16-year-old boys on the soccer team. What do you think happens when you get a bunch of teenager boys together who are playing sports? What do you learn to do? Well, one of the first things we learned to do was we learned to swear in each other's languages. So we could swear in Farsi, we could swear in Hindi, we could swear in French and German and Spanish and so on. Did that mean that those languages were only suitable for swearing? Of course not. It meant that we had an extremely limited vocabulary in which to express our thoughts in those languages. And the same thing is true of patterns. If you only know some of the Gang of Four patterns, or even if you know all of the Gang of Four patterns, or even if you know all of the POSA 2 patterns, and that's it, you're going to find yourself limited when you try to solve larger problems, because bigger problems require a broader range of solution approaches. So don't blame the patterns, blame the lack of knowledge, lack of breadth and depth of knowledge of the appropriate patterns. One of the other issues with patterns, which is kind of ironic because it's a flip side of one of the benefits, is that sometimes patterns will neglect essential implementation and especially optimization details. So you might not adequately address those things early enough in the design to avoid programming yourself into a corner later on. Just as a simple example, when implementing the reactor pattern, which we documented in the early to mid-90s, initially the types of synchronous event demultiplexers that were used were all so-called level-triggered demultiplexers. What that means is as long as there's data available, the demultiplexer will return immediately saying there's work for you to do. The select mechanism, the select function works that way, for example. Later, people began to add other kinds of event demultiplexer semantics into common systems that were so-called edge-triggered, things like dev poll that occurs on some versions of Unix. Unfortunately, the edge-triggered approach only returns when some state transition occurs, which means you have to change some aspects of your pattern interface and certainly your pattern implementation in order to be able to reflect those differences. So if you're not aware of these kinds of things early, and you overcommit yourself to a particular approach based on the patterns that you understand at a particular point in time, you can get burned later down the road. A similar issue arose that we discussed in an earlier module with the singleton pattern, which was originally designed without consideration for concurrency and multi-threading. And when those factors became important as people began to use singleton in those environments, some of the earlier details that had been swept under the rug became very important and actually somewhat limiting without further consideration. You can take a look at this URL to find out more information about edge-triggered versus level-triggered event demultiplexing. Another limitation with patterns is that not all patterns are applicable to non-object-oriented languages. We sometimes like to think that the patterns are pretty interchangeable, that if you understand patterns, you can apply them in Java or C# or C++. And that's largely true with some exceptions. But when you start trying to program in other languages, languages like C or Fortran or Ada or Prolog, much more different from C++ or Java, you find that some of the pattern abstractions just don't really map or don't map in any sensible way. For example, early versions of Ada don't really support the concepts of inheritance and dynamic binding effectively. So common implementations of patterns that rely on those language features have to be radically modified to use them. Likewise, languages like Fortran and C lack certain features. Fortran doesn't really have the concept of pointers. C doesn't really have the concept of destructors or the concepts of classes. You can always mimic these things with the languages using the mechanisms in a building block way, but that can become awfully complicated if you're not careful. Likewise, sometimes even when it is possible to implement the patterns in different languages, they don't get applied in exactly the same way. So for example, if you were implementing iterator in C++, you would undoubtedly implement it in a different way than if you were applying it in C or even in Java, where the abstractions tend to be different. It's the same pattern, but the realization is different. This is not a showstopper, but it's something to keep in mind, that your patterns don't always apply blindly or directly. So to summarize this section, the goal of patterns is not to restrict developer creativity. It's not to have people applying things blindly and rotely in a rigid way by a set of design rules that are not possible to be changed. Nor is the purpose of patterns to try to automate humans. It's not try to replace humans with tools. Instead, the real goal of patterns is to try to codify important insights and experience that comes from humans who have been there before, who have the experience, who've built software, and who've had the good fortune of being able to step back from their work, describe the key interactions, describe the key roles and relationships, describe the key conventions in a way that other people can learn from as they come up to speed in what they're trying to do. Another key important thing to remember about this is that good patterns come from generalizing from real experience. It's very hard to create patterns without that experience. If you read a pattern written by someone who doesn't really quite understand the domain, it usually sticks out like a sore thumb. That's why we use writer workshop methods when we help people become better at communicating what it is that they know, so they get other eyeballs to look and other brains to help consider ways to describe their experience in a way that will be more digestible and understandable by other programmers, other developers, other architects. Many of the software that I've developed and the patterns that I've documented have come out of building lots of real-world systems, middleware, applications, and so on. If you take a look at this URL, you can learn about some of the early experiences we had where we gained knowledge of the effective patterns that later led to the pattern sequences and pattern languages we've been discussing. The final point here is that addressing these limitations with patterns often requires more than just reuse of design. Patterns are fantastic at reusing design, but in a real-world system, you often need more than just design reuse. You need reuse of code.